Hey guys, so this is going to be my last lesson on the synapse today. You know what? You guys can just take a look at Dr. Taylor's PowerPoint on the brain. She did it really easily, really simply. So I'm just going to do the really hard parts, which was the action potential and synapse. And then the brain is really easy. So you can take a look at her PowerPoint for this. I appreciate those of you who are watching these. These are not easy to make. It take a long time to upload. So if you watch them, I'm really appreciative. Thank you very much. So the synapse is the gap between neurons, okay? So here I have a neuron, and there's another neuron. You can see there's this gap between neurons, and that's called the synapse. And the reason why there's a gap between neurons is because you don't want neurons to be connected directly to each other, because if you turn one on, then all your neurons will be turned on, and you don't want that to happen. This neuron is called the presynaptic neuron because it comes before, and this neuron is called the postsynaptic neuron because it comes after. Okay, so you could say the presynaptic neuron is a sensory neuron, which means the postsynaptic neuron would be an interneuron. It's the neuron that comes after, right? So remember, it always goes sensory, intermotor. Okay, so the gap between two neurons is called a synapse. So what we're going to look at is going to be the axon terminal of the neuron, and specifically the synaptic knob. Okay, so hopefully this doesn't take too long. This is kind of easier than what we just did and doesn't take as much time. So this here is the synaptic knob. Okay, so that's what I'm drawing here. And this is going to be the dendrite of the next neuron. So the dendrite of the neuron is that, right? So this is what I'm drawing. And I'm doing the space, the synapse, as the gap between two neurons. Because if this neuron is being activated, then how can it make the next neuron become activated as well, right? How can it do that? Okay, so what you have in the axon terminal, in this synaptic knob, okay, so what you have that kind of is inside of this is a structure called a neurotransmitter, okay? And this neurotransmitter is a chemical messenger. So what is a chemical messenger? A chemical messenger is a chemical that carries a message, right? A hormone like testosterone is a chemical messenger because it carries a message, and the message is to grow hair. But a neurotransmitter also carries messages, okay? And it's made up of chemicals, meaning it's made up of the chemicals on your periodic table, right? To make up this neurotransmitter. And they're found in vesicles in these synaptic knobs at the end of the axon terminal. That's what we're looking at. And basically when, let's say this neuron here, so let's say this is excited, this synaptic vesicle will actually fuse with the membrane and will deposit the neurotransmitter into the synapse. So now you can see I gotta just kind of redraw this. So you guys can see what is happening here is this. Okay, so the action potential reaches the end of neuron. Okay, and when the action potential reaches the end of neuron, the vesicles move. They fuse with the membrane of the cell, and they release the neurotransmitter. Okay, so you're going to get the neurotransmitter being released like this. And these neurotransmitters are now in the synapse. Okay, and when you release those neurotransmitters, that's called exocytosis, okay? So exocytosis means you release the neurotransmitters. Okay, now the neuron that is here, this neuron is at rest, okay? So this neuron has the action potential coming down the neuron. The neuron beside it is at rest, okay? So there are channels on the neuron. So you guys, there are the sodium channels that I just mentioned in my last lesson. There are potassium channels. Okay, and what the neurotransmitter does, so either you're an excitatory neurotransmitter, and if you're an excitatory neurotransmitter, you bind to the sodium channel. And if you are an inhibitory neurotransmitter, you bind to the potassium channel. Okay, so that's what they do. So here, let's pretend this is an excitatory neurotransmitter. Okay, so remember, how was that released? It was released because the action potential reached the end of the neuron. That caused the vesicle that contained neurotransmitters to release the neurotransmitters that it contained. Okay, the excitatory neurotransmitter. How did that happen? I don't even know. And so that then, once that's released into the synapse, okay, the excitatory neurotransmitter binds to the sodium channel. So here's the sodium channel. Now remember, this neuron was at rest, meaning because it's at rest, there's lots of sodium on the outside. That's how we know a neuron is at rest. And there's lots of potassium on the inside, right? That's what we did in our last lesson. Okay, now there's the neurotransmitters. Because they're excitatory neurotransmitters that are being released, they bind to the sodium channel. And when they bind to the sodium channel, they cause the sodium channel to open. Okay, so now all the sodium channels that were closed are now open because that excitatory neurotransmitter bound to it. It binded to it and it opened it. And so now that that channel is opened, sodium rushes in. And guess what? The action potential continues, right? Because all of a sudden, all this sodium and potassium are in there. It was at rest, but now it's at positive 40 millivolts, and the action potential continues from the presynaptic neuron to the postsynaptic neuron, right? So that's what neurotransmitters do. They open channels on the membrane, right? And if you're an excitatory neurotransmitter, you're going to open up the channel, the sodium channel, so the action potential can continue in the next neuron. And that's basically all you need to know. But the thing is you don't want these neurotransmitters to stay in the synapse, right? You don't want that to happen. You want these neurotransmitters, because can you imagine if these sodium channels were always open? Your neurotransmitters would be firing all the time. So what you want to do is you want to break these neurotransmitters down, and that's done by it's called cholinesterase. So cholinesterase is an enzyme that breaks down a neurotransmitter. Okay, and let's say the excitatory neurotransmitter is called acetylcholine. Okay, well, cholinesterase will break down the acetylcholine, that excitatory neurotransmitter. It's breaking it down. And then sometimes you actually reabsorb it. You reabsorb the neurotransmitter and you can actually reuse it. You're going to reuse the neurotransmitter. Listen, drugs, if you take drugs, what drugs do is they keep these neurotransmitters in the synapse for longer periods of time. If you keep the neurotransmitter in the synapse for a longer period of time, then you keep the sodium channels open for a longer period of time and you make your neuron fire, which is why you feel like jumping up and down all night, right? You also have inhibitory neurotransmitters, and they actually cause the next neurotransmitter to stop. Okay, so it stops neural transmission, right? And so those inhibitory neurotransmitters are like alcohol. Like alcohol makes you kind of not, your brain doesn't function as well, and your movements are not as like, you move slowly and things like that. And so that's what an inhibitory neurotransmitter does, right? And it inhibits, and it stops the action potential from occurring. Now, the reason why an inhibitory neurotransmitter works that way is because if you release an inhibitory neurotransmitter, okay, remember this neuron is at rest, okay, and because it's at rest, I have lots of sodium on the outside, okay, and I have lots of potassium on the inside. But if you're an inhibitory neurotransmitter, okay, let's say this in red is the potassium channel, an inhibitory neurotransmitter will actually bind to the potassium channel. And when it binds to the potassium channel and the potassium channel opens, potassium moves out. So now you have all this potassium moving out. So that means that negative 70, okay, so this was negative 70, this was negative 70 millivolts. When all this potassium leaves and you're losing all this, this positive potassium because it's leaving, then it's going to get like so negative, it's going to like get hyperpolarized to negative 90. And at negative 90, the action potential stops, right? And that's how inhibitory neurotransmitters work. So anyways, that's basically all you need to know for synapse, like excitatory versus inhibitory neurotransmitters and how they work and how they cause the action potential to propagate and move to the next neuron. That the acetylcholine is a type of excitatory neurotransmitter. Another excitatory neurotransmitter is adrenaline. Noradrenaline, sorry, is another excitatory neurotransmitter. And basically, that's all you need to know for neural transmission. I hope that helped. Dr. Taylor has posted, like I said before, a lesson on the brain, really easy on the brain, on the different parts of the brain, okay? So like the frontal lobe, which is the front of your brain, and what does it do? The parietal lobe, and what does it do? This is the occipital lobe, and it's responsible for sight. And here's the temporal lobe, which is responsible for sound. So that was posted on hers. So I want you just to forward to that part of the lesson that she posted on the brain. It's just really easy. It's just basic memorization. It's nothing hard. And so I'm going to stop here. Thank you for listening, and thank you for learning. And I hope this helped. And go to Dr. Taylor's PowerPoints to just learn the rest of what you need to know for this unit, which is the parts of the brain.